So energy is the scalar quantity that we use to account for, and it works out very well. Momentum is a bit different. Momentum is actually a vector quantity, and it's also a part of this accounting system where it kind of describes how how much inertia it has, we should say. It kind of describes how much, so let me write the equation down for momentum. It's very, very simple. All right. Remember how we taught, so this is momentum, and all it is the mass times the velocity. That's all it is. And it's a very simple concept and very simple initial equation, and it can become quite complicated in different systems, right? And it's very powerful. So momentum is almost like how much inertia it has, right? Remember inertia from Newton's laws. Inertia is how much energy it takes to accelerate something. Oh, not how much energy. How hard it is to accelerate something, right? We can't just accelerate something without putting it in force, right? We need a force to accelerate something, right? It's related to MA. Well, this is almost how much inertia it has, right? And it's equal to. Can you guys hear my AC on or no?
I can't hear it.
You can't hear it?
I can hear you fine, yeah.
Okay, great. I'm going to leave it on then. I don't want it to ruin the video. So if the AC, if you hear the AC, if the AC is audible, just let me know and I'll turn it off. Okay. If it's audible at all, I would want it off. So just let me know if you hear it. Okay, so the momentum is almost how much inertia something has, right? Because it's the velocity times the mass, right? It's describing how much stuff is moving at a certain velocity, right? It's not just the velocity, it's how much stuff is moving at that velocity, right? And it makes more sense and when we compare it to when we relate momentum to the force. So we take this equation. How can we relate momentum to the force? Now let's look at it. All right. Can anybody tell me how we would relate it? Right. We have m times v. What can we do to this equation to get in the equation for force?
Well, you just need to. Okay.
So the mass doesn't change, it's just a constant usually, right? We don't have a change in mass in most of the systems that we study, right? What can we, so we have V. How can we manipulate V? What is the force equation? Let's write it. We have force is equal to MA. So how can we get the force from the momentum? What operation can we do to this to get it? So all we would really, M and M are the same, right? If we're studying the same system. It's just V and A that are different, right? So how do we relate the velocity to the acceleration? Oh, sorry, I didn't have my chat on, so I didn't see the answer. The derivative, exactly. So if we take the derivative of the momentum, right? Like this, m doesn't change, so it's just a constant. So we have something like this. And this is the derivative of velocity with respect to time, and that's the definition of acceleration. So we find that the force is related to the momentum by the change in momentum. The force is related to the change in momentum. It's equal to the change in momentum, right? And this makes sense, right? If this is almost like a measure of inertia, the change in this inertia, or the how much this object wants to stay in motion at that particular speed, that change would be equal to the force, right? Because how we define the force is something that we have to put in to make it go, to increase its velocity, right? We can't just increase its velocity without, it can't just increase its velocity by itself without some force applied, right? By Newton's laws. So the change in momentum is equal to the force, right? And we say that it's the net force that's equal to the change in momentum. That's what really counts. Not an individual force, it's the net force, right? Hold on a sec. Just give me okay. Sorry guys, I had a phone call. So now we have this force, right? And we're related to its momentum, right? And the change in momentum is equal to the net force. So let's say, so now this is important, right? Because a lot of times it's hard to calculate the forces. If we look at an example 9.1, it describes the force of a tennis serve, right? Now, in real life, how would we figure out what the force of a tennis serve is, right? We would need some advanced equipment, accelerometers, to actually calculate the force, right, on the tennis racket. And what the momentum allows us to do, in a very similar fashion of a similar vein as in kinetic energy, where we could study the initial kinetic energy and the final kinetic energy and figure out the work put in from that, from the initial and final values. We could do something very similar with momentum, where we have the initial velocity of the tennis ball, which is usually 0 in the direction that you hit it at, if you're serving. And we know the initial velocity and we know the final velocity, so we can figure out what the net force on a tennis ball is very easily, right? We don't have to know what happens in between. We could just study the initial and final states and figure out the net force that happens on it. We don't have to account for every single force, right? We could just empirically measure it. And it's very easy to measure the initial and final velocities. I wouldn't say very easy, but it's doable, right? We have a radar gun. So, and we could calculate the force from this, right? So, and that's really the value of momentum. Well, that's one key component of momentum. All right. So we have to be careful. So let's say if we have a tennis ball, we're hitting the tennis ball real quick. All right. So we got a tennis racket and we hit the tennis ball, right? And so the initial, let's say he serves it. So V initial, when he throws the ball up, V initial in the direction of motion, right? V initial has some vertical component because you're throwing it up, but in the direction that you want to hit it, it tends to be 0. So we could assume that V initial is 0, right? And let's just consider that the ball moves in one dimension once we hit it, because we hit it at the top of the throw. The Y component is 0 at the very top, so it's only the initial it's only a velocity and the horizontal component, right? So we have that, and then we say that the V final usually it's given to us at 55 meters per second, and now we could figure out the force on the ball, right? The mass of the tennis ball is easily measured, and it's about 0.06 kilograms or 60 grams. And now we can figure out, and then the question asks, what's the average, what's the force on the tennis ball? And then it asks, is this force large enough to lift a 60 kilogram person? So let's see. So the average force during the whole time that the ball is hit, right, is equal to the change in momentum over that change in time, right? So we would have M1 minus M2 over delta T. And this is the time that the ball is in contact with the tennis racket. And this is usually a couple of milliseconds. And they give us this quantity as 4 milliseconds. That's how long it's in contact. So what's the average force during those 4 milliseconds? It changes because the tennis racket is elastic. So depending on how much the deformation is, the force will change. So, but we'll just take the average force since we only care about the total change in momentum before and after the racket hits the ball. All right. And we'll just plug in the numbers, right? So it's 0 over here. So the change in momentum, I'm sorry, this is supposed to be VF and VI, right? And we plug in the numbers. And when we plug in the numbers, it comes out to 800 newtons, which is pretty high. Let's see if this is enough to lift a 60 kilogram person. Well, with the force of a 60 kilogram person, the weight of a 60 kilogram person, or this weight of 60 kilograms, doesn't matter if it's a person or not, and that's equal to the force times MA, and that's equal to 60 times 9.8 due to gravity. And we find that it's around 600 newtons. It's a little less than 600 newtons. So the force that we apply to a tennis ball, we can lift up a 60 kilogram person, which is quite a large person, right? It's like 180 pounds. So the force that you hit a tennis ball with, that a tennis player hits, it's enough to lift somebody up. And again, all we needed to know was, in this problem, was the mass, the velocity before and after the collision, in this case, and the time the collision took, right? We're able to figure out the change in momentum, or the average force that caused the change in momentum, right? Now, what happens if there's no external force? So if there's no external force on a system, what happens? Well, so if there's no external force, the derivative of the momentum is then 0, right? So what is this saying? It says that the momentum doesn't change. So that means the momentum is conserved, right? So if we consider a system, if we consider this system, right, the tennis racket and the ball to be, and we consider it the momentum of this entire thing, before and after this collision, the momentum never changes. Because the force that the tennis racket implies to the ball, that's a part of the system now. When we talk about the change in momentum, this is an external force. Something that we're not including in our system or in our ideal case, right? So what this means is that we can relate the initial velocities of both objects to the final velocities of both objects. We can calculate its final velocities from its initial velocities. And generally, we will consider a simpler thing. Let's consider two elastic balls hitting each other. So the momentum of this one is this. And initially, these two balls are, let's say they're moving towards each other, right? And they're going to collide. Then they collide. And then what happens after this? If these balls are elastic, what will occur? Anybody?
They transfer the momentum to each other.
Or
will they cancel out?
Well, you can't really say they transfer momentum to each other. What you say is that it changes they change each other's momentum.
Got it.
Right? It changes the momentum. So they hit each other, right? Then they compress, and then from the elastic forces of, let's say, one of those handballs, then they bounce back away from each other, right? And each of these balls changes the momentum of the other. And the reason why I don't say transfers is because I guess you could say transfer. It's okay. It's better to think of as change in the momentum.
Okay.
But anyway, that's just semantics. So what happens? So they hit each other. If these two masses are equal and the velocities are equal, they'll bounce back at the same speed. So, and you got to realize that this is a vector quantity. So this momentum is equal and opposite. So what happens is that when these two balls combine, this experiences a force to reverse the momentum in the other direction. and then the same thing occurs with B. But if you consider this as one system, assume that that the masses and the velocities are equal to each other. If the masses and velocities are equal to each other, what's the total momentum of this system? It would just be the sum, right? Of the system that we're considering, right? Now, if you look, if these are equal, right? The velocities are equal and opposite, right? It's in the opposite direction. So what would be the total momentum of the system? 0, right? Because this momentum will cancel out with this momentum. Likewise, after the collision, there's no external forces. What would be the total momentum of this system?
0.
0 again, right? Even though the momentum of each object is changed, the total momentum stays the same. It's 0, right? It cancels each other out, the two momentums, right? So this is, in the system, the momentum is conserved. So we could say that after the collision, and we'll use a prime here, for after, I'll follow the book's notation. VA prime, let me put a prime over here, plus right? And then it follows that these two are equal to each other if the external force is 0, right? And this is what we'll use. So if I give you the initial velocities and the masses, and maybe we measure the velocity of one of these, we can determine this velocity, right? Or if we have another equation, we can determine the final velocities, right? So now remember that this is a vector quantity. So you could break this down into its components. So in this case, we're working in one dimension, right? But if it was multiple dimensions, the momentum in the x direction would be conserved in the x direction, and then the momentum in the y direction would be conserved in the y direction. So you could treat the two dimensions separately. They wouldn't be related to each other. It's, follows from what we've been doing for the past month and a half. So, and again, this is the momentum conservation. So let's do some example. Let's do an example. So let's do a railroad car. So let's say if we have a railroad car, right? So instead of these balls, we have a railroad car. And one initially, and then before the collision, So generally these problems have two states. One before the collision and then one after the collision. And we just know the type of collision. So we have one railroad car, A. Now VA is, now this is traveling at 24 meters per second. And it is moving towards another railroad car that the VB is 0. This car is stationary. And once they collide, once A runs into B, they combine. So that after the collision, they lock together. And effectively, and they travel at the same speed. Effectively, it becomes one system, right? And we want to figure out what the velocity is here, right? So initially, so there's no external forces, right? So that means that energy, that momentum is conserved. Right. Now, let's do the initial. So P initial, I'll just use an I. And this is equal to MA times BA plus MB times BB. Since B is not moving, it's just equal to MA, right? And then because there's no change in momentum of this entire system, this is equal to the final momentum. And here, the final momentum, maybe I'll write it next to here. This is equal to, since they're both moving at the same speed, it's equal to the mass of both cars times this. Right? Let me just write PI up here. So then we know that PI is equal to PF, and then we just plug it in. So then, and we solve for V prime, and this is equal to VA. So the velocity changes according to this ratio, depends on the masses, right? So MA divided by MA plus MB, right? So that if MB is equal to MA, the new velocity is half the initial velocity of this, right? That makes sense, right? Because what we would be imparting, giving B half of that momentum, right? Or that the inertia will stay the same, right? And if B is 0, it'll continue at the same speed. And that's really this problem. And then the answer, if you plug in all the numbers, it'll come out to be 12. So let's consider one other, another problem. So let's say if we shoot a gun, this is example. So this was example 9.3. And now let's consider example 9.4. So if we shoot a gun, let's calculate what the recoil of that gun will look like. So so let's look at the system, right? We have this gun, right? We have the bullet sitting over here. Initially, the velocities are 0, right? This is one system, right? And we want to, and the problem asks for us to calculate what's the recoil velocity, right? And the rifle, R is 5 kilograms, and B, the bullet, is 0.02 kilograms, right? And then the speed of the bullet leaving the muzzle, the speed of the bullet after the explosion, we'll use prime, is equal to, we measure it to be 620 meters per second. Now, initially it's this, and then, so this is before, and then you set the bullet, you trigger the bullet, and there's an explosion, and then the two items separate, right? The bullet leaves the gun. And this is after. So this is very similar to the last problem, right? Where you have two objects, and then either before or after that they separate, right? They in one instant they are combined, and in another they're separated. Difference is when they occur. So before in this case, they are one system, right? They are one entity basically, and then after it separates into two, right? And this is from the explosion, right? And based on so what's the momentum to begin with? Can anybody tell me? What's the momentum to begin with? It's just the momentum, the mass of the bullet plus the mass of the rifle times its initial velocity, right? What's the initial velocity? 0.